The viral narrative frames this cyborg insect as a triumph of artificial intelligence, suggesting that smarter code has finally unlocked underwater flight. The engineering reality is far more demanding and reveals why we have not seen drones like this for decades despite advances in terrestrial robotics. This story is actually a victory for materials science and power density. While AI software has advanced rapidly, the physical layer sealing electronics against corrosive seawater pressure, achieving neutral buoyancy with heavy batteries on an insect-scale frame, and transmitting data without massive antennas, remains the true bottleneck. Today, we follow the engineering constraints behind the software story to understand why solving the physics of water is harder than building a brain. The primary barrier to aquatic cyborg insects is environmental hostility rather than algorithmic complexity. Unlike terrestrial robots where air offers no resistance or corrosion risk, seawater presents three distinct engineering hurdles that require breakthrough hardware solutions instead of simple software updates. The most critical constraint is protecting sensitive microelectronics from saltwater corrosion and high hydrostatic pressure without adding the mass required to sink a lightweight insect frame. Traditional invasive implants damage muscle tissue by requiring wires to pierce through biological systems, but recent materials science breakthroughs utilize in situ polymerization to create resilient conductive membranes that bond directly to exoskeletons and appendages. This non-invasive approach preserves the insect's natural sensors like antennae for olfaction, while maintaining flexibility, proving high mobility control is possible without heavy protective casings. The research detailing these synthesis and testing methods spans 27 pages of rigorous engineering documentation, highlighting that this is a matter of chemical bonding rather than digital logic. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. In water, gravity and buoyancy are constant forces that must be perfectly balanced for any machine to function effectively. A standard battery pack heavy enough to power an AI processor would disrupt the insect's center of gravity, causing it to sink or float uncontrollably in the ocean currents. The breakthrough lies in maximizing energy density within a microscopic footprint so that the brain does not become a ballast weight. This allows for flight mechanics similar to natural insects while carrying sufficient power for sensing and transmission over extended periods. If we were to use conventional battery technology, the resulting mass would make neutral buoyancy impossible at this scale, rendering the insect useless as an autonomous explorer. The challenge is designing materials that store enough energy without adding the density of lead or steel, a feat that requires rethinking how power sources are integrated into biological frames entirely from first principles of fluid dynamics and material science. The third major hurdle involves the communication blackout inherent to underwater environments, where radio frequency signals standard for land-based drones attenuate almost instantly due to salinity and water density. Transmitting data requires abandoning traditional antennas for acoustic waves or short-range optical links that can penetrate the dense medium without losing signal integrity over distance. Recent developments in specialized hardware demonstrate that secure fleet coordination is possible underwater without surfacing, but this relies on unique physics involving acoustic modulation rather than cloud-based AI processing speeds. The engineering trade-off here is significant. While data transmission speed drops dramatically compared to air or vacuum, it remains the only viable method for maintaining a link with surface control stations when operating at depth. Without these specialized communication protocols and hardware adaptations, any cyborg insect would be an isolated device unable to share its findings once submerged beyond line-of-sight range. This reframing transforms the cyborg insect from a sci-fi magic trick into a tangible engineering milestone for those interested in manufacturing and infrastructure constraints. It highlights that the future of underwater robotics is not about smarter code, but about better materials, tighter tolerances, and solving the physics of fluid dynamics at a micro scale. For viewers curious about how things work, this explains why we can fly drones on land easily, yet struggle to replicate them in water. The environment itself acts as an active adversary that requires physical redesigns rather than software patches. The broader implications touch on hardware supply chains for specialized polymers and infrastructure constraints regarding underwater communication networks needed to support these devices at scale. The sheer volume of research required underscores the difficulty involved. Over 2,000 kilobytes of technical data were submitted just to document the initial validation methods. This level of detail is necessary because every gram of added weight changes the flight dynamics, and every micron of sealant thickness affects flexibility. We are not talking about a simple retrofit, but a fundamental reimagining of how machines interact with hostile environments. The ability to operate in high water stress regions where 72% of global populations face critical resource challenges depends on these small-scale breakthroughs that allow us to monitor ecosystems without disturbing them or requiring heavy, invasive infrastructure. Ultimately, the story is about respecting the physical laws that govern our world rather than trying to bypass them with software alone. The cyborg insect represents a convergence of chemistry and mechanics, where the success lies in the bond between synthetic materials and biological tissue. It proves that when we face hard constraints like pressure corrosion or buoyancy limits, innovation comes from understanding those limits deeply enough to work within them. This approach ensures that future underwater exploration relies on robust engineering rather than fragile assumptions about what technology can achieve without physical support. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.